An electric field. Electric force. Electric force can be an attractive force or a repulsive force. Electric force are propagated or produced in what we call an electric field. For a charged object, this can also create an electric field. So an electric force propagates in an electric field, while a charged object can create an electric field. Electric field. The electric field is represented by what we call an electric field lines. An electric field lines are an imaginary lines that is created to give an illustration or figure out how the electric field lines may interact with each other. So for the case of positively charged, all the electric field lines will radiate outward of the electric charge, while an electric charge of negative will have an inward radiation of the electric field lines. In the case of the two types of charges, in terms of interaction, if there are dissimilar charges, the electric field lines will actually communicate and connect with each other, such as the positive charge radiates outward from the positive charge particle. It will connect to the negative charge particle or the negative charge object. While if there are similar charges, like the two positive charge particles in here, all of their radiating lines going outward of the positive charges will not meet as represented in the other illustration. So remember that the electric charge will always produce an electric field, while the force will propagate in the electric field. So how are we going to calculate the electric field strength? Or for example, in the objects that are presented in here, the formula for an electric field strength is given by the symbol E, which is equal to K multiplied by Q over R square. E here stands for the electric field, while K stands for the electric constant. Q is the charge, while R is the radius, and the radius will again be raised to the power of 2. So this is an electric field line, and the electric field strength. The electric field line was introduced by Michael Faraday, and he said that electric field lines radiates away from a positive charge. So this is a positive charge particle, and the radiation of that electric field line is moving away from the charge, while it radiates inwards or towards the negative charge. And this is how the electric field line looks like in a negatively charged particle. However, the two charges will interact in a dipole particles. For example, here is a positively charged particle and a negatively charged particle. Electrical force. This electrical force or the force can be experienced by any object within the electric field, and that can be given by the formula capital F is equal to Q times E. F here is the electric force in newtons, and Q is the charge in coulomb, while E is the electric field strength given by the unit Newton per coulomb. And we already discussed the value or the formula for E in the previous slide. So again, the electric force can be experienced by any object if that object is found within that electric field. So in this example, we are going to compute for letter A the electric field given by the symbol E in air when it is having a distance of 30 centimeters from a point charge Q1, and a value for Q1 is 5.0 times 10 to the minus 9 coulomb. And for letter B also, the force on a charge Q2 with a value of 4.0 times 10 to the minus 10 coulomb. That is placed 30 centimeters from our Q1, and this is the value for our Q1. And for letter C also, there is another force Q3 or charge 3 with a value of minus 4 times 10 to the minus 10 coulomb. Now this again, Q3 is placed 30 centimeters away from our Q1, but also Q1 is placed 30 centimeters away from our Q2. So for letter C, we are only asked to solve for the force for Q3 and Q1, meaning to say that we will be disregarding the presence of our Q2. And now to solve for letter A, what will be the electric field E in air at a distance of 30 centimeters from a point charge Q1 with a value of 5.0 times 10 to the minus 9 coulomb. For example, this entire area is air and this is our Q1. From Q1 up to 30 centimeters away from that, there will be an electric field E in here. So we wish to solve for that electric field, and that can be solved by the use of the formula E is equal to K times Q1 over R2. That will be substituted with K will be 9.0 times 10 raised to the power of negative 9 newtons times meter square over coulomb square. Then the value for Q1, which is 5.0 times 10 to the minus 9 coulomb. We can now cancel out the coulomb unit, but since this is coulomb square, that one will have coulomb left. So that will be divided by the R, which is 0.3 meter raised to the power of 2. So the value is 0.5 kilo Newton over coulomb. So kilo is simply multiplying this one by 1000. So that is the value for our electric field in air that is positioned 30 centimeters away from charge number 1. For letter B also, the force on a charge Q2 is equal to 4.0 times 10 to the minus 10 coulomb. That is again placed 30 centimeters away from our Q1. So a while ago in the previous slide, we were solving for the electric field when Q2 is only air. Now this one, there are two charges, and we will be solving for the force interaction between Q1 and Q2 that is separated 30 centimeters apart. For the calculation of the force, we will be making use of the formula Fe is equal to E times Q2. So now our E, which is equal to 500 newtons over coulomb, multiplied by our Q2, which is equal to 4.0 times 10 raised to the negative 10 coulomb. The value of Fe there is equal to 2.0 times 10 to the minus 7 Newton, or simply equal to 0.20 micronewton. That is positive value, so meaning to say it is directed away from our Q1. And finally, letter C, the force on a charge Q3 is equal to negative 4.0 times 10 raised to the power of negative 10 coulomb. That is placed again 30 centimeters from Q1 in the absence of Q2. So this is still Q1 and this is now Q3 instead of Q2. So the distance is always the same, that is 30 centimeters apart. And to solve for the force between Q3 and Q1, so we have the value which is the electric field of Q1 multiplied to Q3, the charge Q3. So the value will be equal to 500 Newton per coulomb multiplied by negative 4.0 times 10 minus raised to the negative 10 coulomb. So we can cancel out coulomb and the value will be equal to 2.0 times 10 to the minus 7 Newton, or that will equal to negative 0.20 micronewton, Since it is negative in symbol, that force is directed towards Q1. So this is the conceptual summary for our electric field. Any charged object will create an electric field, while electric force can be experienced and can be propagated in an electric field. Now, our electric field is pictured by the means of electric field lines, and our electric field lines is introduced or developed by Michael Faraday. Now, electric field can have electric field strength, and electric field strength becomes higher with more electric field lines. An electric field will interact with other electric fields. So, electric field lines will radiate away from positive charges and radiates towards negative charges. So, they both positive and negative charges electric field lines will interact, especially if there is a dipole, like one is positive charge and the other one is negatively charged. So electric field lines is not a two-dimensional but rather a spherical or three-dimensional that can be illustrated in some materials.